So if we're going to be looking at exponential growth and decay, or generally for data that changes over many orders of magnitude, which this is, then we're going to be using a log linear graph or a semi-log graph. And what is that? So normally on the x-axis we have the normal scale. These are just your normal numbers, so often this might be the time. Then on the y-axis, crucially, is in a logarithmic scale. So this could be, for example, the number of cells. And so what effect does this have of transforming the data on your y-axis into the corresponding logarithms? So it allows us to look at changes over many orders of magnitude. You can simply fit more on your graph. So for example, if we've got a linear graph, so that's kind of a normal, say we've got normal and normal numbers, then let's imagine, so let's have the scale here going up to 100, so then 10 will be down here somewhere. So here is, so if we're going from here to here, then this is a 10-fold different. I think you can agree. Like this. But then if we were to go on a log scale, then log of 1, so that's equal to 10. Log 2 is 100. Yeah, so then, and then log of 3, this is 1,000, but that's only a little bit more on the graph. So we can, so here, from 1 to 2 is a 10-fold difference. So that's the first advantage. So we can fit a lot more on our graph. And it's especially good for exponential growth and decay because a side effect of transforming it into logarithms is that the kind of curvy part of this exponential function gets straightened out by transforming it into logarithms. And so that can be more convenient if you want to, interpolate a certain value, for instance, work out how much time it will take for your culture to grow in size a certain amount, for instance. So bacterial growth curves. So we know that bacteria, cells double every 30 minutes maybe for a happy E. coli culture, something like that, and this is exponential growth. So if we did a linear graph of a bacterial growth curve, what we'd see, so if we have cell number on the y-axis and time on the x-axis, so this is the linear graph, then you get a curve that looks something like this. So this is the exponential bit of the growth. This is what our exponential growth function looks like, and then it kind of flattens off. But then, and you can experiment with doing this for yourself. Then if we have the log of the cell number on the y-axis and the time in kind of not transformed into logarithms on the x-axis, then the graph ends up looking something a bit more like this. We've got a nice straight line here and then plateau. So this part of the graph here is the, we call that the log phase. So this is the exponential growth part of the graph. And then here, this is the plateau. We call that stationary phase. The cells aren't really growing. So this is when the culture has run out of nutrients. And so this is much more convenient to, for example, if we want to know how many cells there are at a given point in time, that's much easier using a nice straight line than a curvy line like that.